Welcome, everybody. Thank you for being here. It's good to have you. Good to have you here with us. Get yourself ready. Grab yourself a pencil or a pen. Anything you choose to write with is fine. Don't forget your notebook. Need something to write on. This is math from the void. Math coming at you out of nowhere. And today we have a problem from the 2006 AP Calculus BC exam, which is still admittedly about 20 years ago now. Kind of crazy. Some of y'all weren't even born yet, which is even crazier. This is a BC question. However, the only BC component is at the latter half. Part C is definitely a BC type question asking about a Taylor polynomial. Part D, I believe, is also a BC topic, although an AB student could do it if they understood Euler's method. That being said, AB students, you might just want to give yourself half the time and do parts A and B if you're so inclined. In any event, give yourself some time to do this on your own. If you're a BC student, give yourself about 12 to 15 minutes. This is a complete problem with many different types of questions in it, so I think it'll take some time. If you're an AB student and you're doing parts AB, hey, look at that. Maybe give yourself literally like 6 or 7 minutes. It shouldn't be that difficult to answer parts A and B. Okay, so when you're ready, you can come back and join us and see how we do it here. Let's get started reading the problem. We need to consider this differential equation, dy dx, and it's sort of an unpleasant dy dx that we wouldn't want to find the original function for, not at this level of calculus anyways. It tells us that y cannot equal 2, that's important. Let y equals f of x be the particular solution to this differential equation, and we do have an initial condition that f of -1 equals -4. In other words, the point -1 comma -4 is on the original function. And let's get started with part A. Part A says to evaluate dy dx and d squared y dx squared. So the first derivative and the second derivative at -1 comma -4. Now dy dx is obviously going to be very easy to evaluate. We just straight up plug in these values. This is going to be 5x squared, well, x is -1, -1 squared is just 1, minus 6 over, the y value is -4, so this is going to turn into 5 minus 6 on -6, which is just 5 plus 1, or 6. So that is our dy dx. Now let's find d squared y dx squared, which is going to take a little bit of work because we have to take the derivative of the derivative to get the second derivative. So let's first rewrite the derivative in a way that is a little bit more clear for us to take a derivative of that. So this is a little bit more clear. And now if we want to take the derivative, we can just sort of use like the chain rule. So we can say d squared y dx squared is equal to 10x, of course, that part's easy. And then we have plus 6 because we're multiplying the -1. And this will become y minus 2 to the -2 power. But then we have to multiply by its derivative, dy dx. So if we're plugging in -1, -4 again, this is going to go to 10 times -1 plus, maybe we can write it in the fraction form again, 6 over y minus 2 squared. And then this is times dy dx, which we happen to already know the value of, so I'm not gonna use the time to write out the entire expression for dy dx. We just solved what it is at that same point, so we're good. Whoops, I should put the y value in. That's a -4. Okay, so this is the same as -10 plus 6 times 6 is 36 over negative 6 squared is negative 6 times negative 6, also 36. And so we get that the second derivative is equal to negative 9. I think those are very approachable. Even if you're an AB, it's pretty easy to do that. Kind of like a little implicit differentiation for the first problem here. Or for the first part of the problem. Okay, part B. I love when they ask these types of questions. Is it possible for the x-axis to be tangent to the graph of f at some point? Explain why or why not. Well, let's think about this. If we have a point at -1, -4, where is that located? That would be located, let's move it over here. That would be located down here. And we know that the first derivative there is 6. It's going upwards. And we also know that the second derivative is negative, so it's doing it with like sort of a concave down shape. So the question is, does that work? Is it going to sort of smack the x-axis at some point, right? So if the x-axis is tangent, that means two things. That means not only does the y value equal 0, but it means that the derivative equals 0 as well. So here's the question, can dy dx equal 0? Well, if x equals some number, we don't know where it would be at, but y equals 0, this would be 5x squared plus 3. This has no solution. And because it has no solution, that means there is no x value. Use some math language here. There does not exist an x such that y equals 0, which means it's at the x-axis, and dy dx equals 0. So I'm not saying that the derivative is never 0 or that the function never goes flat. I'm saying that it doesn't go flat at the x-axis, which is what it would mean for the x-axis to be tangent. So this means y equals 0, but also it means dy dx equals 0. Impossible. Cannot be done. So that requires a little bit of thinking that maybe an AB student wouldn't be a huge fan of doing. However, that's how you solve it. Yep. Oops. All right, let's look at part C. Part C says find the second degree Taylor polynomial. Thank goodness it's just the second degree about x equals -1. First, let's write out what that looks like. We're going to call it T2 of x. And we can say that f of x is approximately this Taylor polynomial. This is going to be f of -1 plus f prime of -1, or we can say dy dx at x equals 1, times x minus -1 to the first, technically divided by 1 factorial, but that's just 1. Then we have f double prime, or in other words, dy squared, or d squared y dx squared at x equals -1, over 2 factorial times x minus -1 squared. So if we write that out, we're going to get -4. We already have these values, plus 6 times x plus 1 minus 9 over 2 factorial times x plus 1 squared. And that's really it. So the Taylor polynomial was really easy because whatever degree we're using on the Taylor polynomial, that's how many derivatives we need to be sort of knowing information about. And we already know the first and second derivatives from part A. So as long as you did those correctly, and even if you didn't get those correct on part A, if you made a calculation error, but you plugged the numbers in appropriately where they belong, you're still going to get quite a lot of points. You're just not going to get the point for the full answer. So you probably will still get 1 out of 2 points, even if you plugged in the wrong information, because you knew that you were supposed to plug in the first and second derivative, even though you may have calculated it wrong. Okay, I'm not saying you for sure calculated it wrong. I'm just saying even if you did calculate things wrong in part A or part B that are required for parts C and D, using the terms correctly, even if they're the wrong terms that you're using, it still does award you some credit. Okay, part D, which is the more labor-intensive part, says use Euler's method starting at x equals -1 with two steps of equal size to approximate f of 0. So this is a method of using a tangent line, but then kind of adjusting the tangent line as we go. So let's start off with what we know for sure. We know for sure that f of -1 equals -4. So if we were to write an equation of tangent line, because we know f prime of -1 is 6, we can write y plus 4 equals 6 times x plus 1. We could also say that y equals 6x plus 2 if we move stuff around. So what we want to do is we want to travel along this tangent line just a little bit, because we're using two steps of equal size to go from x equals -1 to x equals 0. So we're going to step back a bit, and we're going to say, what if x equals -0.5? Which gets us a little bit closer to 0. Then our y value is approximately, or I should say that f of -0.5 is approximately 6 times -0.5 plus 2, which is going to give us -3 plus 2, or -1. So now we're going to use the point -0.5, -1, to approximate the derivative at -0.5 is going to be approximately 5x squared, so I'll put it as 1/2, minus 6 over the y value, which is -1, minus 2. That is just using the derivative equation, you guys. This is dy dx. The derivative at this point is dy dx. We have an x and a y, so there's our derivative. This is going to be 5 over 4, minus 6 over -3. So this is going to be 5 over 4 plus 2, or we can just call that 13 over 4. Now, we're not done yet. We've approximated the slope at this point. We're going to write a new tangent line, right? We're going to say that y plus 1 equals 13 over 4 x plus 1/2, x minus -0.5. And if we want to rearrange that a little bit, I'm not sure how comfortable you guys are with these fractions. Get comfortable with the fractions. So this is going to be plus 5/8. So we're going to say that f of 0 is approximately 13 over 4 times 0 plus 5/8, which is 5/8. So what we've kind of done on this tangent line, I'm going to just sort of sketch it. So we have something that's going like that. We have a point that's exact. Let's go this way. We have a point that's exact, and what we're doing is we're using a tangent line, and we're saying, oh, instead of using the tangent line all the way out here to say that's our approximation, what we've done is we've sort of cut that portion and said we're just going to use the tangent line up to here, part way, and then we're going to adjust the tangent line according to this tangent line here. So we're going to get it a little bit closer now. It's going to change direction ever so slightly. I don't even know if I can capture that properly. It's going to change direction ever so slightly, and so our approximation here is a little bit better than if we had just continued to use that approximation. You see how it's closer to the curve on the part that's bent right here? Hopefully you can see that. So we've used Euler's method by adjusting the tangent line as we go, and that helps us find a more accurate approximation for the function. Of course, a Taylor polynomial is even more accurate, but this is a way of doing things without polynomials. Maybe Euler wasn't so inclined to use polynomials when he was developing this method. Okay, but like I said, this is a complete, thorough differential equation problem where you ironically don't have to anti-differentiate and find the original function, even though when they give you an initial condition, like 90% of the time you have to integrate and find the original function, but not all the time, most of the time. They did ask us this tricky question about the x-axis being tangent. They can ask stuff like that on the AP exam. They want you to think more than they want you to work in some of these questions. they really want you to think, what does it mean to simply say x-axis is tangent? It means we're a point on the x-axis, y equals 0, that's for sure. And since it's tangent to the x-axis, which is a flat line, that means the derivative is 0 at that point. Other than that, we had some BC topic, Taylor polynomial and such. I think that is very easy and standard to figure out for a student, especially since we've done in parts A and B, we did the first and second derivative. It really gives you the coefficients of the polynomial pretty easily. Okay, I think that's enough blab out of me, especially with all this math jargon you guys might not like. Hope you learned something, BC students. Keep studying. Test is approaching, and I'll see you guys next time in the voice.